Morning, afternoon, evening, whatever. Every day is the same. Um, anyway, we're nearing the end of the semester, and today we're going to talk about Chapter 11. This is the last chapter that we have homework in. This homework, though, is just for bonus, so enjoy. All right, so we're going to talk about fundamental theorem of finitely generated abelian groups. Finite abelian groups, anyway. This can be extended to any abelian group that has a finite number of generators, whatever that means. So if I might, this is FTFAG means fundamental theorem for finite abelian groups. There could be another G there, generated, okay? But let's just talk about not finitely generated groups yet, because we haven't gone through the generators relations section. Anyway, abelian groups are nice. Okay, they are the direct product of cyclic groups of prime power order. And not only that, if you look up the isomorphism class of each, there's more or less a unique way to write it out. If you write them from sort of descending order by their parts, the orders of the subgroups, right, where we're using an internal direct product, but up to isomorphism's external direct product of cyclic groups of the form Z mod N, right, or Z mod P to the K, where P is a prime. Why is this useful? Well, it allows us to essentially write down immediately all the possible abelian groups of a given order, and it's based solely on the prime factorization of the order of the group. So 24 is 8 times 3, right? So if we look at the only possibilities for the prime power order of the subgroups that are going to be the factors of our internal direct product, the only possibilities for the prime factor 2 have to do with the partitions of its exponent here, 3. So we look at the partitions of 3. And I mean this 3, right? This 3, not that 3. Okay. Well, you've got 3, right? You've got 2 plus 1, and then you've got 1 plus 1 plus 1. That means there are only 3 possibilities for the cyclic subgroup that, or cyclic subgroups that correspond with this prime power factor of the order 24. So what we get here is, if G has order 24 and is abelian, let's use the notation of the book, abelian, then G is one of the following: either Z mod 2 cubed plus Z mod 3, or Z mod 2 squared plus Z mod 1, or 2 to the 1, plus Z mod 3, or the only other possibility is if all the highest order element is 6, right? Order 6. That means all these guys are Z mod 2s, and that's a Z mod 3. Okay, so the unique representation here of the cyclic groups has to do with breaking up the prime power order. So certainly I can switch the order of the Z mod 3 anywhere. I could also make the Z mod 3 and the Z mod 2, for instance, into a Z mod 6, right, by isomorphism. So there's a way to take sort of the highest order elements and use that as the cyclic subgroup in, say you want to do it in descending order. Here, for example, this is Z mod 4. Z mod 4 plus, or external direct product Z mod 3 is isomorphic to Z mod 12, since 4 and 3 are relatively prime. But if you want to be systematic about it, just write down all the factors of the group corresponding to the prime factors of the order of the group, and then you won't make a mistake. Okay, so basically, how do we do this in general? Well, it's what we just kind of did, all right? So say we wanted to figure out what the group is. Say I'm just given a group. Here's the example that I want to try to prove. Okay, I've just, here this is some group under multiplication mod 65. We could show directly that it's abelian, but of course multiplication modulo something, that's going to be abelian. So this is a finite abelian group. We would have to show, I guess, that it's closed, but just pretend I know. So how could we figure out which one it is? Now, we know that the order is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, the order is 16. So it is a prime power, right? 2 to the 4. There are partitions of 4 number of possibilities for G, right? And we could use a process of elimination to find the isomorphism class, or we could use something called the greedy algorithm. This is outlined in your textbook, but here's in a nutshell, pseudocode. Okay, compute all the orders of the elements of the group. All right, that's easier said than done. But say I figure out all the orders, then take any element of maximum order. So say there's an element of order 16, right? Well, then we know what the answer is. G would be Z mod, or isomorphic to Z mod 16, since it would be cyclic itself, right? But say the highest power or the highest order would be something else. I don't know what it is. We'll figure it out when we get there. Okay? Take that element, right, and form its cyclic group, right? So that you know that element and all of its powers, and you sort of tick those off the list of possible values in G that you need to represent. Okay, set the first iteration to 1, right? Now, if G sub I, in this case G1, has the same order as G, then we stop, right? Because we found the representation of G as a product of cyclic groups. Otherwise, we're going to set I to its next iteration and go to step 3 and do this iteratively until we get to the order, until we have a representation of G as a internal direct product of cyclic groups in this way. So we select an element AI that's a maximum order such that the order, of course, needs to be less than or equal to the order of G divided by the order of the previous iteration group, and that these elements, none of them are included in the and so we also want to show that its cyclic group that generated by that element is not in one of the previous iterations of G. So in other words, we want to be able to show that G sub I is an internal direct product of the previous iteration times the cyclic group there. And to do that, we would need to show that the intersection between G sub I minus 1 and this cyclic group is the identity. But that's what this is asking or saying, right? We set Gi to be that, okay? Every time we do this, we sort of take away more elements, and what's greedy about it is we're doing it in the biggest chunks possible. Once we get down, once we find that G sub I has the same orders as G, then we would stop. Okay, so let's see if we can apply this to here. And of course, we can use a little bit of greedy algorithm, a little bit of process of elimination to get at the answer the quickest. So note the order of G here is 2 to the 4th power, which means G is equal to, or isomorphic to, either Z mod 16, Z mod 8 plus Z mod 2, Z mod 4 plus Z mod 4, Z mod 4 plus Z mod 2 plus Z mod 2, or a bunch of Z mod 2s. Okay, the first one and the last one would be the easiest to decide. If all group elements have order 2, right, then this is the answer, right, this last one. If all the group if there's at least one that has order 16, then we know that don't do that. Then we know that the group is, then we know that the group is cyclic. Hold on a second. All right. Sometimes this tries to do some weird stuff. Okay, so once again, if the orders of the groups are only 2, then we know the answer is this. If there's any of them has order 16, then we know it's this. If any of them, if we don't have 16, but one of them has 8 as order 8, then we know this is it. Okay. The only hard ones is if the highest power is 4. Okay. So just because, you know, I'm evil, we look computing the orders. Right, we see there is no of order greater than 4. Okay, so we can already eliminate this one and this one from the list. Okay, and actually there is an element of order 4. What is it? A sub 1 is the number 8. This has order 4, which means G is not equal to this one. So we have either this answer or this one, right? So we need to figure out which one of these, this one or this one. Okay, so let's try the greedy algorithm. A sub 1 is 8. The cyclic group generated by the element 8 is 1, 8, 64, and 8 cubed modulo, what's the modulo 65? What's 8 cubed modulo 65? 57 is a cyclic group of order 4 there. Okay, so now find another element of maximal order. So this means that G1 is this. Okay, but the order of G1 is less than the order of G, so we keep going. Okay, and we find A2 is an element of order 4, so maximal order. In this case, it is element 12, for instance. Okay, so that it and its powers up to the order of the element -1. So we need to find A2 is 12 because 12 is not in A1 or G1. Say that way. Okay, and 12 squared is 144, which is congruent to 14 mod 65. Is that right? Okay, maybe. Okay, that is not in G1. Okay, that's 12. And we need then 12 cubed is not in there as well. And if we do that out, that's not in there either. So that's enough to say that A sub 2 is 12. Okay, this is equal to 1, 12, 14, and 12 cubed mod 65 is 38. Okay, so this here is the next subgroup, but then G2 would then be G1 plus this A2. So let's remember what G1 was. It was the subgroup generated by 8, subgroup generated by 12 is the other one. We see that then order of G2 is the order of G, so we stop. Okay, and each of these has order 4, which gives us our solution. Okay, but that it's actually equal to this internal direct product. It's not really obvious, but that's the case. Okay, that's what the fundamental theorem of finitely generated abelian groups, how it would work, I guess. Okay, another thing that's cool about this is if G is a finite abelian group, then it's CLT, right? So this means that finite abelian groups are CLT, right? So if you have a factor of the order of the group, then there's a subgroup with that order. It's because we have cyclic groups, and cyclic groups are CLT. Okay. So, for instance, for example, let's find a subgroup of order 20 in a group of order 200. So, without kind of doing all of them, let's just pick at random. So, 200. What is that? That's 20 times 10. It's 25 times 8, right? So 5 squared times 2 cubed. So there are, let's see, how many partitions of 2 are there? There's only 2. 2 partitions of 5 times, we saw there were 4 partitions of 3. Is that right? 3, 2 plus 1. No, 3 partitions of 3. Right? Yeah. There are 6 possibilities for six possible groups we could do, right? 2 that have order divisor of 25, and 3 that have divisors of 8. Okay. So let's just pick one and see if we can find a group of order 20. And we can do it for all possible groups, but I'm just going to pick one at random. Let's do, let's say Z mod 5 plus Z mod 5 plus Z mod 4 plus Z mod 2. Okay? And I can actually find a cyclic subgroup of order 20 in this group here. Okay, so let's take H to be subgroup generated by 1, 0, 1, for instance. Okay, so that has order. The lowest common multiple of the orders of each of these: 5, 1, 4, and 2. Right? Lowest common multiple is 5 times 4, so that's 20. Okay. What if there was a harder one? Let's do, say, z mod 25 plus z mod 2. So this would be the first example. I don't know. Let's pick another one. All right, and so let's take H is subgroup determined by taking an element of order 5, okay, and doing the internal direct product of that with an element of order 2, and another element of order 2. Okay, so the way that the orders work is, everything in here is times everything in there times everything in there. It makes up the definition of this internal direct product, which means this has order 20. Okay, and that's how all these things work. All right, I think with what we've done here, we've shown enough that I hope you're able to do all of the homework for this section. This section's homework is optional. You can do it, and I'll only count it if it helps your homework scores. But I hope that you do it. It's kind of fun to work with finite abelian groups. The next video will be proving the fundamental theorem for finite abelian groups, and I do hope you watch that as well. But I think now you can go ahead and start on the homework. All right, thanks guys.